Hi guys, this is A2 Chemistry, Analytical Chemistry, and we are doing chromatography. Question 1. Chromatography relies on either partition or adsorption to help separate substances. Briefly explain how each method brings about separation. How does partition bring about separation? It is the ratio of the solubilities of a sample component in the stationary and mobile phases. So when a solute is dissolved in the stationary and the mobile phase, the ratio of its solubility is the reason for partition taking place because it will be soluble more in one of the phases and less in the other. Next, we have adsorption. So it is the ratio of the affinity of a sample component for the stationary phase relative to its solubility in the mobile phase. So adsorption is basically the affinity for the solid stationary phase and its ratio with the solubility for the mobile phase. So if it is more soluble, it will travel a greater distance. If it's more adsorbed, it will travel a lesser distance. So next we have the table shows three different techniques of chromatography. Identify which separation method, partition or adsorption applies to each. So paper chromatography. So in paper chromatography, the principle of separation is partition. Next, in thin layer chromatography, the principle of separation is adsorption. And finally, in gas liquid chromatography, the principle of separation is once again partition. The diagram represents the output from gas liquid chromatography carried out on a mixture. So the output shows us that there are two components in the sample, X and Y, and it asks us determine the percentage of each of the two components X and Y in the mixture. So in order to determine the percentage composition of each of these, what we would need to do is we would need to measure the base and the height of both the triangles X and Y using a scale, and the values we obtained for X for the base would be 1.3 centimeter and for Y is 1.4 centimeter. For the heights, for X, the height is 2.0 centimeters and for Y, the height is 2.4 centimeters. Now that we have the base and the height of both the triangles, we should apply the formula for area of a triangle, which is half into base into height. So area of x would be half into 1.3 into 2.0, giving us a value of 2.0. Then we would apply the same formula to find out the area of y, and here we would have half into 1.4 into 2.4, and we obtain an area value of 1.68. Next, in order to find out the percentage of x, we would place area of x in the numerator, which is 2.0, divided by sum of areas of x and y, which is 2.0 plus 1.68, and we multiply this by 100, and we end up with a percentage value of 43.6%. For area of y, we can do 100 minus 43.6, or we can use the same calculation as the calculation for x, that is percentage of y is equal to 1.68 divided by 2.0 plus 1.68 into 100, and in both these ways we will get the same percentage value of 56.4%. So percentage of x is 43.6% in the sample, and percentage of y is 56.4% in the sample. Question 2. In thin layer chromatography, better separation may be achieved by running the chromatogram in one solvent, then turning the paper at right angles and running it in a second solvent. The chromatogram below was produced in this way. So according to this chromatogram, when solvent 1 was used, the spots traveled upwards, and when solvent 2 was used, the spots traveled towards the right. And the question asks us, ring the spot which was insoluble in solvent 1. That means that particular spot would be no, at the position where the sample was applied. That means on X, because solvent 1 moved the spots upward, and this spot would not have moved at all. So if we look at the spots right now, this is the position of the spots after solvent 2 was used. So when solvent 1 was used only and solvent 2 was not used, this spot was here, this spot was here, these two spots were here, this spot was slightly here, and this spot was here. So these arrows show where the spots would have been positioned if only solvent 1 was used. So ring the spot which was insoluble in solvent 1. So as you can see, this spot, the one that has just been ringed, is the one that would not have moved only when solvent 1 was used, because it would have been on the X position where the sample was applied, and hence it is a spot that must be ringed. Next, label as A and B the spots which were not resolved using solvent 1. So, two spots that were exactly on the same position when solvent 1 was used are these two spots, A and B, because both of them point towards the same position according to the arrow that we drew just right now. Uh, that is just a single position on the chromatogram, which was separated into two separate spots upon using solvent 2. Question 3. In thin layer chromatography, better separation may be achieved by running the chromatogram in one solvent, then turning at right angles and running it in a second solvent. The chromatogram below was produced in this way. Okay, they've shown use of solvent 1 is upwards and use of solvent 2 is towards the right. So if we resolve this chromatogram for just the use of solvent 1, so this spot would have been at the X, this spot would have been here, both of these spots would have been here, and this spot would be over this spot when only solvent 1 was used. So the question asks, how many spots were visible before solvent 2 was used? So the positions of the arrows are 1, 2, 3, and 4. So we would have 4 spots being visible when only solvent 1 was used. Next, ring the spot that did not move in solvent 2. The spot that did not move in solvent 2 is the one that is positioned exactly where it was when solvent 1 was used, which is this spot. And next, how many spots traveled further in solvent 2 than they did in solvent 1? So, if looking at the first spot from the bottom, it did not even move in solvent 1. It moved this distance in solvent 2. So, this is one of the spots. Looking at the second spot, the distance moved using solvent 1 was this much, while the distance moved using solvent 2 was this much. So the distance moved while using solvent 2 was greater than solvent 1. Looking at the third and the fourth spot, the third spot moved very little in solvent 2. However, the fourth spot, which is in the same line as the third spot, moved a greater distance in solvent 2 than it did in solvent 1. So this is the third one. And the other two spots can be seen to have moved more in solvent 1 than in solvent 2. So we end up with three spots that have moved more in solvent 2 compared to solvent 1, especially the first one, which has not moved at all in solvent 1 and has just moved in solvent 2. So the answer for this part is three spots. Question 4. The diagram shows the results of two-way paper chromatography of a mixture of amino acids. So when solvent 1 was used, the spots moved upwards. When solvent 2 was used, the spots moved towards the right. So the positions of the spots when only solvent 1 was used would be this spot would be on the X. These two spots would be on the same position here. This third spot would be exactly where it is right now. The fourth spot would be here, and the fifth spot would be here. So these are the positions of the spots relative to use of only solvent 1. And the question says to answer these questions, you need to indicate clearly on the diagram above as directed in the question. Put a U next to the amino acid that travel furthest in solvent 2. So this is the amino acid that would be found to the extreme right of the chromatogram, which is this amino acid. So this is the one with the, it says U, not W. W is the other part of this question. So we put a U here. Next, put a ring around two amino acids that were not separated in solvent 1. So this and this, they were exactly at the same position when solvent 1 was used, according to the arrow we had already drawn. So these are the two amino acids that must be ringed. And put a W next to the amino acid that was very soluble in both solvents. So an amino acid that is very soluble in both solvents is the one that travels the furthest in both. So the first spot only travels in solvent 2. The second and the third spot in the same line travel more in solvent 2 than in solvent the third spot. The second spot travels more in solvent 1. The fourth spot that is lying exactly above the X did not even move in solvent 2. The fifth spot has a greater distance moved in solvent 1 as well as solvent 2 as indicated by these lines. So this is the distance moved in solvent 1 and this is the distance moved in solvent 2. And the last spot has a greater distance moved in solvent 1 and a smaller distance moved in solvent 2. So the only one with a greater distance moved in both the solvents is the one with the blue lines placed on it, and this is the one we mark with a W. Question 5. A mixture of amino acids can also be separated by thin layer chromatography. Identify the mobile phase and the stationary phase in this type of chromatography. So, the mobile phase would be an organic solvent, and the stationary phase is Al2O3 or SiO2 coated onto a glass plate. What is the process by which thin layer chromatography can separate a mixture? The process by which mixtures can be separated using TLC is adsorption. Question 6. Paper chromatography and gas liquid chromatography both rely on the partition of compounds between mobile and stationary phases. Identify the mobile phase in paper chromatography. It would be an organic solvent. Next, suggest what type of a liquid is used for the stationary phase in gas liquid chromatography. It has to be a non-volatile liquid that has a high MR. So we can call it a non-volatile high fraction alkane. So C16 or C17 containing alkanes could be used here. Both these techniques can be used to separate mixtures. State what you would measure in order to distinguish between the components in the mixture. In paper chromatography, we would measure the RF value, and in gas liquid chromatography, we would measure the RT value. RF stands for relative front, and RT stands for retention time. Relative front is the ratio of the distance traveled by the solute divided by the distance traveled by the solvent, and retention time is the time spent inside the glass column of the GLC apparatus. A mixture of three compounds was analyzed by paper chromatography using a non-polar solvent. The resulting chromatogram is shown. Identify which compound is responsible for each spot. So we've got three compounds in which we've got one or two substitute groups attached and a benzene ring in all of them. So benzene ring being common can be eliminated because it is the same thing in all three compounds. So what we are left with are the COOH group in the first compound, the CH2OH group in the second compound, and two COOH groups in the third compound. So looking at the polarity of these groups, we have a non-polar solvent being used. So the one that is the most polar will travel the least distance. So since the third compound has got two COOH groups, the third compound would be the one that is placed at position 3 because it will travel the least distance. Now we're left with COOH containing and CH2OH containing compounds. So both of them are polar, COOH being a carboxylic acid, CH2OH being an alcohol. So the next thing we need to do is calculate their MR. So COOH would be 32 for 2 oxygen, plus 12 would be 44, and H 45. And for CH2OH, it would be 16 for oxygen, plus 12, which is 28, and the 12 is for carbon, and then 3 hydrogen, so 31. So the greater distance moved would be the one with the lower MR, so that would be for position 1, and the one with the higher MR would be the one positioned at spot 2. So the order in which these compounds are separated is: the first compound is at position 2, the second compound is at position 1, and the third compound is at position 3. Question 7. A mixture of volatile organic compounds X, Y, and Z can be separated in a gas chromatograph. Their identities can be confirmed by measuring their different retention times and comparing to the known values. A gas chromatogram is shown. So we have three components, X, Y, and Z. Suggest what is meant by the term retention time. So it is the time spent in the glass column, or rather we can say it is the time taken by the components of a sample to exit the glass column from the time they had been injected into it. So this is how you define the time spent inside the glass column. Next, give an example of a carrier gas used in gas chromatography, it has to be an inert gas. So examples of inert gases are nitrogen, or you can name any noble gas. So noble gas may include helium, neon, argon, etc. Z spends the longest time in the chromatography column. Suggest why this might be the case. So if Z is spending the most time in the column, it means it is the one that is the most soluble in the stationary phase. So Z is the most soluble component of the sample in the stationary phase and might have the same intermolecular forces as the stationary phase. So that is why it would spend the longest time inside the column. Next, explain a possible limitation of gas liquid chromatography in separating two esters such as ethyl methanoate and methyl ethanoate. So ethyl methanoate has a molecular formula of C3H8 and O2, and methyl ethanoate also has the C3H6. C3H6. Ethyl methanoate and methyl ethanoate both have the same molecular formula, which means they've got the same MR and they are both esters. So that could be the reason why they can't be separated. So both of them have the same MR values and the same functional group. Hence, cannot be separated in GLC. Next, a student works out the areas underneath the three peaks in the chromatogram. Assuming the areas underneath the peaks are proportional to the masses of the respective components, what percentage of the original mixture was made up of the organic compound X? So we would calculate this part as area of X, which is 22, upon area of X plus area of Y plus area of Z into 100. And this would give us a percentage value of 28.95%. So the percentage of X in the sample is 28.95%. Question 8. A mixture of three different compounds, J, K, and L, was analyzed by thin layer chromatography using a polar stationary phase and a non-polar mobile phase. The three compounds all have similar molecular masses. The resulting chromatogram is shown. So spot 1 traveled the furthest distance in a non-polar mobile phase, so it has to be the most non-polar, and 3 traveled the least distance, so it has to be a polar component. And the question asks, identify which spot corresponds to each compound. So in compound J, we have got a ketone group and we have got a carboxylic group. In compound K, we've got 1 and 2, two carboxylic groups. And in compound L, we've got a single ketone group only. So here the role of the non-polar part would be played by ketone, although ketone is polar, or let's call it less polar than carboxylic acid, and the more polar group here would be the carboxylic group. So the one having two carboxylic groups is the one that would travel the least distance. So that would make the one travel to spot 3 as compound K. The one that would travel the greatest distance would be the one without any carboxylic group in it, which would be compound L. And the remaining compound would be the compound in the center, which is compound J. So one travels the greatest distance because it only has a ketone group. Two is placed in the middle because it has got a single ketone and a carboxylic group. And the least distance traveled is by the compound having two carboxylic groups. Explain your answer to one. So the one with the more polar groups travel the least distance, and the one with the least polar groups travel the greatest distance. So we would write the compound with the most polar groups would be the least soluble in the mobile phase and would travel the least distance. This answer can also be written with respect to the least polar. So the compound with the least polar group would be the most soluble in the mobile phase and would travel the greatest distance. So both way the answer is correct. What is meant by the term RF value? RF value stands for relative front, and relative front is described as ratio of the distance traveled by the solute to the distance traveled by the solvent. Question 9. An aldehyde, an alkane, and a carboxylic acid, all of similar volatility, are mixed together. The mixture is then analyzed in a gas chromatograph. The chromatogram produced is shown. So X comes out first and Z comes out last. The separation of the compound depends on their relative solubilities in the stationary phase, and the stationary phase is a liquid alcohol. So if it is a liquid alcohol, that makes this polar. So the most polar would be the one that comes out the last, that would be the carboxylic acid. The least polar would come out first, that would make it the alkane, and the one in the middle would be the aldehyde. So we have already identified which peak corresponds to which organic compound. Next, complete the table to suggest which compound in the mixture is responsible for each peaks X, Y, and Z, and explain your answer by reference to the intermolecular forces of the compounds. So peak X corresponds to an alkane because it has London's dispersion forces present in it. So making it non-polar. Next, we would have compound Y, which is the aldehyde, as it has dipole dipole attraction present, which is a stronger intermolecular force than the London dispersion forces. And the one that would come out the last would be the carboxylic acid, because carboxylic acid would have hydrogen bonding present, and it would be the strongest intermolecular force of the three compounds. A student calculates the areas underneath the three peaks in the chromatogram. The area underneath each peak is proportional to the mass of the relative compound. Calculate the percentage by mass in the original mixture of the compound responsible for peak Z. So this would be area of peak Z, which is 47, divided by the sum of the three areas, which would be 19 plus 32 plus 47. And we multiply this by 100 in order to get a percentage value. And this is calculated to be 47.96%. So the sample contains 47.96% of compound Z. Question 10. An alkene, a carboxylic acid, and a ketone, all of similar volatility, are mixed together. The mixture is then analyzed by gas chromatography. The gas chromatogram produced is shown. So J comes out first and L comes out last. The separation of the three compounds depends on their relative solubilities in the liquid stationary phase. The liquid stationary phase is an alkane. So the liquid stationary phase is non-polar. So the one that is the most non-polar will come out the last, which would make it the alkene. The most polar would be the carboxylic acid, that would come out first, and the one in the middle would be the ketone. So we've already identified which compound is which. Next, complete the table to suggest which compound in the mixture is responsible for each peaks J, K, and L. Explain your answer by reference to the intermolecular forces of each compound. So compound J is the carboxylic acid due to the presence of hydrogen bonding in it. So it will be the one that is the least soluble in the alkane. The next compound K would be the ketone, because it will not have as strong an intermolecular force as hydrogen bonding, but it would have dipole attractions present. The most soluble of the three compounds would be compound L, which would be an alkene, and it would be the most soluble in the alkane because the alkane is non-polar, and the alkene would also be non-polar, and being non-polar, it would have London's dispersion forces present in it. A student calculates the areas underneath the three peaks in the chromatogram. The area underneath each peak is proportional to the mass of the respective compound. Calculate the percentage by mass in the original mixture of the compound responsible for peak K. So in order to calculate the percentage of peak K, we would have the area of K, which is 18, divided by the sum of the three areas, which would be 46 plus 18 plus 28. Multiply this ratio by 100 to obtain a percentage value of 19.57%. This means that the percentage of K in our sample is 97.57%.